Uh, okay, so here we take a look at how to interpret the partial derivatives with respect to x and y in terms of the graph of the function. So if you remember back in Calc 1, for a single variable function, the derivative gives you the slope of the tangent line or the instantaneous rate of change at the specific point on the graph. Similarly, for a function of two variables, so again taking some specific point in the xy plane, and then looking at the corresponding point in the graph, right? So like for some xy value, so say the xy value is here, and then the function value is calculated at this point in the graph. So if we're looking at the partial derivative with respect to x, imagine taking a plane that's parallel to the x-axis and cutting through the graph so that it produces this cross-section through the specified point. So then the cross-section will cut out this light blue curve here, and the partial derivative with respect to x calculated at the specific point will give you the slope of this tangent line that's highlighted in pink here. Similarly, if we take a cross-section through the graph and through the specified point, but this time parallel to the y-axis, then it's going to cut out a cross-section now in the y direction, and the slope of this tangent line is given by the partial derivative with respect to y. Basically, if you do a cross-section parallel to the x-axis or a cross-section parallel to the y-axis, then you can think of the partial derivatives again as slopes of tangent lines or instantaneous rate of change, similarly to how we did for single variable functions. So in example 2 at the bottom of this page here, it describes a function that's similar to the function that's being visualized in these two diagrams, right? So if I take the function 4 minus x squared minus y squared, and so let's quickly draw it in the GeoGebra, so that you'll see that it's an upside down paraboloid. So 4 minus x squared minus y squared, right? So it's this upside down paraboloid. So the function is similar to what's being shown in this diagram here. And if we calculate the two partial derivatives with respect to x and y, you get minus 2x and minus 2y. And if I select the point 1 comma 1, then the partial derivatives at this point are both equal to negative 2. So basically, if you imagine that these two diagrams are demonstrating the calculation shown in example 2, then this negative 2 is supposed to represent the downward slope of this pink line on the diagram on the left, and then this negative 2 is representing the downward slope here on the tangent line on the right. So that gives you an idea of how the partial derivatives are represented in terms of the graph of the function.